I would like to start. Let me give you an outline of today's lecture and then also a little bit of a preview. So today I'm giving you the little bit more of a bird's eye view and an overview into precision lattice QCD calculations, mostly for flavor, but not just. And then in the second half of today's lecture and also for tomorrow, we'll delve a little bit more into the semantic EFT and discretization, how to treat discretization effects. And on Friday will be all about muon G-2. So that's my plan. And before I start, I wanted to kind of take a little bit of the temperature in this room, and maybe you've already had these questions, so then you're practiced. So by show of hands, how many of you are working in lattice QCD? Wow, okay, the vast majority. How many of you are working in more generally lattice field theory, but not QCD necessarily? Okay. How many of you are not living in Euclidean space? Okay. Okay, fair. Good. Okay, so you have a pretty good background, and maybe you know most of what I will tell you about. In that case, sit back, relax, and enjoy the show. One more question. How many of you have delved in detail into semantic EFT and studied it in detail? Oh, a few? Okay. Okay. Maybe you're worried about what I mean by detail. So how many of you know about Kurt Szymanczyk? Know who he was? Studied his papers a little bit? Okay. All right. So we'll learn some things. Okay. So let me start with a big picture, starting with particle physics and what are the open questions in flavor physics. And one often shows this some version of this plot showing the spectrum of fermion masses, which spans many orders of magnitude, even forgetting about the neutrino masses. Where's this pattern coming from? And there's this very famous question that was alleged to have been asked by Isidore Rabi when the muon was finally correctly identified, though I haven't really been able to follow those historical references. But it generally goes as to why do we have three generations. We know that that has to do with CP violation, which is one of the essential ingredients in the matter-antimatter asymmetry, why we exist. But without at least three generations, we wouldn't have that. But why three? Why don't we have four, etc.? The origins of the fermion masses, are they really Higgs-Yukawa as is predicted in the standard model or something else? The mass hierarchy, the structure of the mixing matrices, the Kobayashi, Kabibo, Maskawa, and PNNNS for the neutrino sector. So all of these are problems that we don't really understand. Fine-tuning problems that we don't understand the origin of. We don't know if we have identified all of the sources of CP violation and how that explains the matter-antimatter asymmetry, etc. So lots of open questions, despite the fact that the standard model is the most successful theory that we have, has stood the test of time. And we haven't really been able to positively identify how to extend it and where exactly it breaks. Okay, but that is what we need to do in order to achieve a deeper understanding of nature. So it's not really about the excitement of new physics. It's all about deepening our understanding. Okay, so starting with the first question here, the origins of fermion masses, we have some intriguing new information, and that comes from the LHC, where now, and this is, by the way, surprising, that the ATLAS and CMS experiments have been able to measure the Higgs decay rates as precisely as they have, even having measurements of Higgs decay into muons at this precision level. That's a little bit unexpected. They were thinking that this would come later, maybe at the high Lumi LHC, but experimentalists are very smart. And as a general rule, whatever the projections are, the experimental successes are usually better than those projections. And this is no exception. So what is remarkable about these plots? It's remarkable that the decay rates really follow a straight line. Why is that remarkable? Because what we see here is, so this is a measurement of how the Higgs boson couples to fermion masses. In the standard model, the Higgs boson's coupling to the masses of all particles is always proportional to their mass. In the standard model for fermions, it's the Yukawa coupling. And the reason why this is remarkable is the W and the Z bosons get their masses from the fact that the standard model theory is a spontaneously broken gauge theory. So the W and Z boson masses come from the gauge principle. I mean, it's baked into the formulation of the theory, if you want, that the W and Z boson masses arise. The fermion masses are tacked on. The Higgs-Yukawa part of the standard model is tacked on. Let me go here right away. And it accommodates the fact that the standard model electroweak sector is a chiral gauge theory. And within that chiral gauge theory, after electroweak symmetry breaking, then the Higgs boson can also give fermions their masses. But this is the first real test that we have. The experimental measurements are the first real quantitative test of this. And it seems to be that even the Higgs-Yukawa sector of the standard model is holding up to experimental scrutiny. So this is a relatively recent development that is important to note. And what does this have to do with lattice QCD, you might ask? Well, we have already achieved pretty good precision on the experimental side. These error bars are going to come down. And once these error bars come down with a high Lumi LHC and potential new colliders that measure these decay rates more precisely, then the theoretical predictions of these decay rates, where you have to include, of course, also loop corrections, etc., will depend on also the parametric inputs, including what are the quark masses. To confront this picture, we need to know what the quark masses are. And the best way in which we can know the quark masses is, of course, lattice QCD. So lattice QCD features in here as essential inputs in the determination of the quark masses, as well as the precision extraction of alpha sub s, and you'll have lectures about this next week, so I won't really talk about this here. And maybe not so future anymore. In order to make sense of this experimental program, we also need to know the PDFs much better. And there is now a rather large and growing effort in lattice QCD to access PDFs in some form, and I will not talk about that. This is just to say that lattice QCD is not just in the traditional weak decays of mesons, which I'll spend some time talking about relevant. But a lot of the precision demands, which now energy frontier experiments at the LHC are turning into precision instruments. And then we also need Lattice QCD. And these are the simplest inputs, and there are more, of course. So this is in some sense, these new experimental measurements are deepening the mystery, at least to me. This was not something that needed to happen this way, and are also giving us more work to do. In particular, we really do need to improve our knowledge of the quark masses as well, and need the community to accept those. Okay. So then we talked about, I already alluded to the structure of the mixing matrices. So we have a hierarchy in the Kabibu-Kobayashi-Maskawa matrix, which is that the diagonal elements, up, down, strange charm, and top, bottom, that these matrix elements are near 1, and off-diagonal matrix elements in this mixing matrix that is, of course, arises from the weak sector of the standard model, become smaller and smaller as you go more off diagonal. And it is in the mixing in the first and third generation that the CP violation lives. And it's small also as indicated here. So this is a very different hierarchy than the mixing in the neutrino sector. And this is probably because actually, even though the standard model also accommodates neutrino masses, that's even more of a just parametrizing the unknown. So this is another hint that perhaps the fermion mass generation for neutrinos and charged fermions is different. So it seems that the charged fermions are compatible, at least for now, with the Higgs-Yukawa mechanism. And that means that the CKM matrix elements are also probing the Higgs-Yukawa sector, because it is arising from that. And so understanding this may trickle back into also a better understanding of the Higgs boson properties. We'll see.
Could you move the board a little bit to the right?
Okay, and this was not a question. That was, of course, a comment for visibility. Let me also say that questions are welcome at any point. Okay, so let me continue. So flavor physics is the place where one searches for indirect signs of new physics. The energy frontier is where we smash things together and look for new stuff coming out. That's one of its jobs, but also precision, as we just indicated. And in precision physics is where we can look for indirect signs of new physics, either by finding processes that are completely forbidden in the standard model, or by finding evidence of processes that perhaps are suppressed in the standard model and are either further suppressed or are enhanced by beyond the standard model physics. So that is one of the games where Lattice QCD plays an essential role by uncovering by allowing us to uncover the desired information by having precise calculations of the QCD effects. Okay. So one of the motivations of this is already on that slide, is the muon G minus 2, where you have maybe seen a recent announcement that came out in June of a new measurement, the final measurement by the Fermilab experiment. So the Fermilab experiment started its runs in 2017. That was the first revolution, was measured in 2017, and they concluded their collection of data in, well, actually 2024, they just did some more measurements of the magnetic field, but the data collection, the collection of muons concluded in 2023, and they released their final analysis on June 3rd in a scientific seminar at Fermilab. Prior to the Fermilab experiment, there was the Brookhaven experiment. Prior to the Brookhaven experiment, there were the CERN experiments, all using a very similar method to measure the precession of the spin of a muon in a magnetic field, and from which they then measure the anomalous magnetic moment of the muon. And this is now measured to an astounding less than 130 parts per billion. So that's precision, right? And again, you might ask, what does Lattice QCD have to say about a muon's property? And we will talk about this on Friday, but it is the muon indirectly coupling to quarks because it carries charge and can talk to photons, and photons talk to charged particles that affect the magnetic moment of a muon, and we'll talk about that, as I said, on Friday. So this is also a job for Lattice QCD, confronting this precision. Okay, so the traditional quark flavor Lattice QCD calculations, and I'll show you how traditional this really is illustrated here. So we measure some weak decay process in experiment and then confront that with standard model theory, where there may be some CKM factors that we want to determine or we want to test, and we need to know the hadronic matrix element, which is illustrated in this cartoon here, and it is the hadronic matrix element that is computed in Lattice QCD. We have this factorization here with some known factors. Once this is input, then we can test the standard model, or we can use these measurements to extract standard model parameters such as the CKM matrix elements or quark masses, etc. Okay. So let's start with a history view. Everything in QCD happened in the 1970s, including Ken Wilson inventing Lattice QCD at the same time at which QCD was discovered as the correct theory of the strong interactions. And then very soon after, Mike Kreutz's seminal works on understanding how to do simulations of Euclidean quantum field theories, moving on to QCD. And it was very early on, already in the early 1980s, that people realized that this would also give an avenue towards computing weak matrix elements. And the first review of weak matrix element calculations in Lattice QCD was in 1989, maybe, which is before many of you were born. And then in the early 2000s were the first Lattice QCD simulations that included realistic C-quark effects. So we've been sharpening our tools for a long time, which is what this is telling you. And here is a first review by Steve Sharp, who will be celebrated next week in Berkeley at a fest. And of course, he's well known in the field. And this was one of the first reviews of Lattice QCD calculations of beloved hadronic matrix elements, decay constants, and even epsilon prime, mixing matrix elements, etc. in 1989. And all of this was still burdened by the quenched approximation, which I will really not talk about here because we're not going to be talking about the past. I just wanted to put the present in context. Now, going back to the early 2000s, once we learned how to do calculations with realistic C-quark effects. Realistic means that the C-quarks still had masses that were too heavy, but in the region where chiral perturbation theory, and I'll come back to that, gives us access to realistic extrapolations, once we can include C-quark effects, then you can see an alignment of lattice QCD calculations compared with experimental measurements. This is a ratio of a variety of different quantities in spectroscopy and also matrix elements, where before there's always a 20% or so error and a spread associated with this by comparing lattice QCD with experiment, and we find alignment. And then this also started us in the game of first lattice QCD predictions. If you look here at the archive number, you can see that the archive numbers are very similar, but the CLIO-C measurement of the D plus decay constant came after the first lattice QCD calculation with commensurate precision. In that sense, this is a genuine prediction. The B sub C spectrum, again, was predicted in lattice QCD before the B sub C meson was discovered by the CDF collaboration and the shapes of form factors. So once we have realistic lattice QCD calculations available to us, then pretty much everything is a prediction if you do your job correctly, and you can confront theory with experiment and learn something new. So that was in the early 2000s, and since then we have sharpened our tools even more, and we're now in a situation where the QCD part of lattice QCD calculations has reached or exceeded experimental precision, and it is now QED corrections that are the dominant source of theory error for comparing with experimental decay rates, and I'll come back to that. So that's a milestone, and that's certainly something to celebrate, and also means that now we have more work because now we have to compute those things. And okay. So you've already had some lectures on spectroscopy, on computing correlation functions. I think Jeremy has gone over that. So I'm not going to talk about how this works. When we compute matrix elements, it's the same spectral decomposition that gives us masses and decay constants, and also gives us, and when we compute three-point functions, then matrix elements and form factors, etc. The point that I'll be spending most of my time at is this one here. We do these calculations on a whole bunch of different gauge field ensembles that have different parameter choices, and repeat them in order to then control the systematic errors. When you have precision, you have to worry about absolutely everything, and you have to worry about all parameter variations. So that's what we will focus on here. Okay, so all the parameter variations come from first all the approximations that we make when we formulate lattice QCD, the finite lattice spacing, the finite box, finite spatial box, and finite time extent, which are all coming with adjustable parameters. And then, because we're theorists, we can also choose our quark masses and tune them as works best for us. Whereas in the experiment, of course, they're stuck with the masses that nature gave the particles. And so we have a whole bunch of adjustable parameters, and that seems to be, that's kind of wild. You know, vary everything, and then what? How do we get to nature's point? What guides us? And the good news is that there's a lot about QCD that we can understand analytically, and you already had some beautiful lectures from Max about finite volume effective theory that is intimately connected to QCD being a confining theory, and S-matrix principles, analyticity and unitarity, that gives us a description of finite volume effects, the famous exponential suppression of finite volume effects that around which much of the precision in meson physics is built, but also much beyond that, how to deal with multi-particle systems. So I won't be talking about this, but certainly precision lattice calculations are heavily leaning into this. How do we have control over discretization effects? Well, it is the combination of asymptotic freedom and renormalizability that allows us to write down the semantic EFT, and we'll talk about that in detail. For dealing with effects from mistuning light quarks, we have the underlying QCD features is chiral symmetry of the theory, which is spontaneously broken, which gives us chiral perturbation theory. And then for heavy quarks, we have heavy quark symmetry, which gives us heavy quark effective theory and non-relativistic QCD, all EFTs of QCD that don't have anything to do with lattice, but that we use in order to understand both discretization effects for heavy quarks better and also quark mistuning effects in the heavy quark sector, etc. So these are leaning into the EFTs of QCD, then gives us an ab initio description, because these parameter choices, these extrapolations or interpolations, are now guided by theory. They're not extrapolations into the wild. Okay, so that's very important, and this is what allows us to claim precision. Okay, so just a brief review over flavor symmetries in QCD. Again, I might be telling you stuff you already know very well. So chiral symmetry is broken spontaneously by the chiral condensate, which we can compute in lattice QCD as well, and then also explicitly broken by the fact that the quark masses are not zero. So we have a remnant isospin symmetry, which is mildly broken, and SU3 flavor symmetry, and all of these are important tools for our lattice QCD calculations, as well as making connections to phenomenology. Heavy quark symmetry is a symmetry of QCD in the limit where the quark masses become infinitely large, around which then is built the effective field theory, heavy quark effective theory, which, by the way, was developed both in the continuum and from a lattice perspective, kind of simultaneously, contemporaneously. Okay, I will be returning to some of this a little bit later. So let me lean into the description of discretization effects, and we'll circle in more detail as we go on. So these things you know, we have to resolve the typical momenta of the particles inside the bound state, and that means that we need to have lattice spacings that are small enough to resolve these. And if that is the case, then we can build a semantic EFT. Schematically, it's shown here. So our lattice calculation, our calculation of some lattice physical quantity on the lattice, matches the continuum plus discretization effects that for on-shell quantities are guaranteed to disappear with the positive power of the lattice spacing, roughly speaking, with the typical momentum in the problem. So this is the leading order. These are the leading order discretization effects for modern fermion actions, and gauge actions disappear with usually with n equals 2. Sometimes there's alpha S suppression for that, and we'll talk about this in more detail. So this is very important for guiding the continuum extrapolations. However, underlying this, then we need to have simulations. We need to generate gauge field ensembles at multiple lattice spacings and then take the continuum limit. And it is now accepted in the field that 3 really is the minimum. More is better, but it's not just the number of lattice spacings, it's also the range of lattice spacings, which gives you then access in the data also to higher order truncation effects that you want to have some numerical evidence for and then confront them with your theoretical expectations. So for the precision level that challenges 1% or less, this is very important. Okay, the point I'm making here is that numerical prowess is of course an important ingredient. Without numerical simulations, without access to large-scale computational resources, and good algorithms, and optimized code, and that large-scale effort, precision is doomed. However, without a lot of theory as well, precision is also doomed. So the two have to work hand in hand together. Okay. So we'll talk about heavy quark physics quite a bit. I'll be returning to this, but here's the big picture. So in the days when people started looking at the early days of when people started looking at heavy quark physics, which as you already saw, this was something that was immediately interesting. The simulations were, even in the quenched approximation, were limited in the lattice spacings that were reachable to where generically the lattice spacings were larger than the Compton wavelength of the B quark, which is another way of saying that discretization effects are basically completely unmanaged. A times m is larger than 1. There is no expansion that you have. However, it was also very quickly realized that the system that we are actually studying in the lattice is we're not looking at the quark degrees of freedom. We're measuring, in the end, correlation functions of hadrons and extracting information about hadrons. So if we look at a B meson, it actually is an extended object that is resolved by even a coarse lattice spacing. And the B quark here functions in the limit where the B quark mass goes to infinity, just functions as a color electric source. And the dynamics of the light degrees of freedom is more similar to what you have in a light meson, and you have to deal with the fact that you have something that is nearly static here. So this separation of scales, whenever we have a separation of scales, suggests an EFT treatment and understanding heavy quark symmetry, understanding heavy quarks as color electric static sources, and then how quark mass effects allow them to wiggle around. That EFT description, if we have a heavy light system, is heavy quark effective field theory, and if we have a heavy system, a non-relativistic system, is non-relativistic QCD. And so we can have a lattice, a discretized heavy quark effective theory, or discretized NRQCD, on which we can use these as our discrete fermion formulations on which we then compute which we then use to compute, correlation functions, etc., on the same gauge field ensembles as for other formulations. So developing NRQCD, developing discretized NRQCD, the development of heavy quark effective theory was actually a joint venture, both from a continuum and a lattice perspective. And the problem with this is that the continuum limit is complicated. In fact, in the NRQCD formulation, really, you can't formally take a continuum limit. The mass must serve as a cutoff here, and the continuum limit here is thought to be by adding higher order terms to in the non-relativistic expansion and seeing that your physical answers don't change, are insensitive to the cutoff. So the continuum limit is complicated, and the matching and renormalization is complicated, so there is a limitation in precision. We'll be talking in more detail about this relativistic approach to heavy quark physics, which and then leads us back to, now that we have the computational resources, to this approach here, whereby one uses a highly improved light quark action, fully the same light quark action as for light quarks as for heavy quarks, and this is allowing us to breach the percent barrier for heavy quark physics as well. So we'll be talking about this in the semantic context a little bit more detailed. Okay, so we'll come back to this. This is just a big picture overview first. So CKM metrology, we want to determine CKM matrix elements. There are lots of processes to which we have access for lattice QCD calculations, decay constants, form factors, and all of these indicate existing programs of calculations. And I'm not really mentioning baryon, of course, nucleon matrix elements here as well. There's some baryon processes as well. So all of this is true for baryons too, but for mesons, the calculations are simpler and we can get to precision a little bit quicker. Okay, so this is now quite established, and most everybody is using CKM matrix elements where lattice QCD calculations of the underlying form factors play an important role, and I'll show this in the following. So let me start with leptonic decays of light mesons, of kaons. I've already showed the equivalent of this, albeit for the rare decay. So this is the charged kaon decaying via charged W boson into a charged lepton. This is a 3-level decay, and at this level we have factorization, whereby the decay rate can be factorized into hadronic part, which is then parametrized by the decay constant, the hadronic matrix element, and the leptonic part. And then the decay rate depends on all of these different parameters, including a VUS. And we compute the decay constant and then use the experimental measurement to get VUS out. Seems pretty straightforward, but it's not quite that straightforward because QCD isn't the only game in town. We also have to deal with QED, because in fact these are charged particles, and everything that carries charge talks to photons, and that also includes the underlying particles that are both in the C and in the valence here. Everything carries charge, so everything talks to photons. And experimentally, of course, you can't ever measure just the kaon decaying into a lepton and a neutrino. There's always photons present, So experimentally, this decay rate is actually photon inclusive, and we need to then, if we want to make contact with experiment, we also need to know the QED corrections. So I'm assuming that we know how to compute the strong isospin breaking corrections. Those are much more straightforward. Okay. So under QED corrections, factorization doesn't hold anymore because photons can certainly be exchanged between charged particles, but they are small enough that we can still phrase them as a parameter like that. So this is then the full picture. We don't just need to know the decay constant, we also need to know the electromagnetic corrections. For kaons, because chiral perturbation theory works and we have a lot of phenomenology, these electromagnetic corrections can be estimated phenomenologically using chiral perturbation theory and then some modeling. And in particular, looking at the ratio of a charged kaon to a charged pion decay, some of these corrections cancel, and the calculation of these phenomenologically estimated effects is maybe not entirely unreliable. As indicated here, so there are now first lattice QCD calculations. Well, first, it's actually been a game that people have been playing for over 10 years to compute the electromagnetic corrections. And here is a result from the RBC, a recent result-ish result from the RBC UK QCD collaboration showing how you have showing a calculation that also includes, also addresses the various sources of systematic error. This quench here refers to quenched QED, not QCD, by the way. And so, it's a very nice looking systematic error budget. Could be improved, is in good agreement with phenomenology, and all of these different results are in pretty good agreement with one another. Their question? Okay, go ahead.
What does quenched QED mean?
Very good. So quenched QED means that generating QCD ensembles is expensive. So the QCD ensemble will have gluons and C-quarks in them, and the C-quarks, of course, carry color charge. And when we do a quenched QED calculation, then the C-quarks are electrically neutral. So the photons will not be able, don't couple to the C-quarks, and so that's an easy thing to do. You can take your existing QCD calculation, your existing QCD gauge field ensembles, and add, photon fields to it. So the valence quarks are charged when you then compute correlation functions, but the C-quarks aren't. You can do the full thing, of course, that's more expensive, where you generate QED plus QCD gauge field ensembles from the start. And then there are other ways in which we can get after QED C-quark effects by simply computing additional correlation functions to, that are disconnected, that give you access to the C-quark bubbles as well. So that becomes more complicated, and I'll talk a little bit more about that on Friday as well. Okay. Good question. So for semileptonic kaon decay, there's a similar story. And here I'm showing the example of neutral kaon decaying into a charged pion and a charged lepton. In that case, the final state pair carries, both. You have two final state particles that carry electric charge, which means that there are also now QED interactions between the final state particles that have to be included in addition to the kinds of QED effects that you had in the leptonic case. And generically, the QED effects are at the 1% level, which is kind of where you expect them, but enhanced here because of this Coulomb effect for the neutral meson decay. Okay, so in this case, there are some first attempts at computing the electromagnetic corrections in lattice QCD. It becomes more complicated, of course. So, quantifying this better is one of the important things that we need to do as a community in order to also understand some of the puzzles around first row CKM unitarity tests. Okay. But the rest of the story of factorization, except for QED corrections, works the same way. And with phase space, one then parameterizes the hadronic matrix elements as a form factor at Q squared equal to 0, but that can be expanded as well. Okay, so instead of a decay constant here, we have a form factor to compute. Instead of a 2-point function, we have a 3-point function to compute, and a matrix element involving a weak current. But it is similarly straightforward, at least for light mesons. So I hope that you've all heard of the FLAG collaboration. That is a group of lattice field theorists who review the field, and in particular is in the business of reviewing flavor physics results. They have an expanding portfolio that now also includes nucleon matrix elements. And as more quantities, come into the precision family, their portfolio will continue to expand. And so they provide reviews of physical quantities. It's also a really nice resource for methods, for different actions and approaches and so on. I highly recommend that you download it or bookmark it and use it as a lookup as well, and finding out about other people's, what the ensembles are, what their properties are, etc. It's a really nice resource for that. So they put out these reviews, and there is some color coding in here, kind of like traffic lights. Green, fully green is go, and red, there's something of concern here. For example, only one lattice spacing or not enough lattice spacings, or some other properties of the underlying simulations that basically say that perhaps this is not a quantity that should be included if you want to have precision. So if you look at the most modern results, I mean not entirely always, but most modern results now include 4 flavors in the C, so also including the strange. So 2 + 1, up, down, degenerate, that's the 2, and then +1 for strange, +1 for charm. Charm quark effects in some cases can be estimated separately, but as you're pushing to sub% precision, they need to be quantified, at least for heavier quark quantities. So the ratio of decay constants, the FLAG average, weighs in at less than 2 per mil. That's pretty impressive. And this is why QED effects are now the thing. So QCD, improving just the QCD calculation of these decay constant calculations isn't really going to improve our knowledge at all. So if you're a student coming into this, then actually thinking about QED corrections or radiative decay calculations, this is where these calculations are heading. You don't want to compute ratios of decay constants other than to verify that you understand your calculation. So that now becomes a way to understand your calculation and not a new relevant result. And similarly, even though there are fewer results, but the precision is pretty similar for the kaon form factor. And so again, this is why I was emphasizing QED effects. Now, what is the big picture? What are the reasons why these errors are so small? Well, we have now, and many groups have now, libraries of gauge field ensembles at a range of lattice spacings where the C quarks are at their physical value or very near their physical value, so that we just need to add some small corrections to interpolate to the correct values. And then using improved light quark actions as well, so discretization effects are small, and doing the calculation in a smart way where the renormalization, where you compute quantities that aren't renormalized or use ward identities or compute the renormalizations entirely non-perturbatively with the corresponding precision, so you don't have to guesstimate perturbative higher order truncation effects in perturbative matching, at least for these very simple quantities. So these are the features that allow us to push to below the precision, the 1% precision level, and here way below even 5 per mil level. And the same features, the same principles also hold for then heavy quark physics. Okay. So there's an interesting puzzle in first row CKM unitarity. So I showed you the CKM matrix earlier. What I didn't emphasize is that, and I think you probably all know this, is that the CKM matrix has to be unitary, and that unitarity gives us many conditions on the matrix elements. The first row, the sums of the absolute value squares of the first row has to add up to 1. And you can see that it doesn't quite, depending on which inputs one actually uses here. So depending on which inputs we use, there's a 2 to 3, for a while there was a 5 sigma tension here. Surprising. But this is exactly, the thing to look at. And the question is, are there things here that we've underestimated? Are there effects here that we don't understand? Or are we seeing the breaking of the standard model? It's hard to do this, but this becomes an interesting investigation. So I might be biased, but what is a possibility here is that the best determination of VUD comes from nuclear beta decay. Now, the experiments are old and long-standing. The nuclear theory is also quite well established, but there's been some recent development in understanding some of the structure-dependent electroweak corrections here that have actually shifted VUD quite a bit. So more work is needed in understanding these. Whether or not these effects can account for this tension, we don't know. I emphasized that for the kaon form factor, so that would yield these bands here, this vertical band here. The KL3 form factor is straightly proportional to VUS. Once you take the experimentally measured decay rate and our form factor calculations, that turns into a determination of VUS. So that's the horizontal band. I mentioned that the electromagnetic corrections there are only computed phenomenologically. So if there is something there, then that can also, address this puzzle. But even more interesting, there is also a puzzle if you look at, forget about VUD from nuclear beta decay, take the lattice calculations of the ratio of the decay constants and the lattice calculation of the KL3 form factor together with their respective experimental measurements. I told you how, in particular, for the ratio here, we already have pretty good lattice calculations of the radiative corrections as well. And you can see that it's quite far from unitarity too. So it doesn't quite fit. None of this quite fits with unitarity. The effects are small and puzzling, and I haven't even added the information from tau decays yet, which also gives us access to VUS. There's also puzzles there. Whether these puzzles have anything to do with new physics, with unexplained phenomena, we don't know, but there is more for us to do here. Yeah?
You say that the VUB is roughly 0.
Yes.
But to what, 0 can be, to what precision it is 0? Does it...
So VUB is of the order of 10 to the minus 4,
Okay.
so it's not relevant here. Good question. Okay, so let's move on to semileptonic demeson decays. So take the kaon and replace it with a demeson. That means that the strange quark is replaced with a charm quark. And here, this process now gives us access to VCD, the CKM angle VCD that's kind of like VUS in terms of its magnitude. And now we are dealing with two more effects here. So the demeson is much heavier than the light degrees of freedom. So there is the kinematic range is much larger. So instead of just focusing on a form factor at a certain value of q squared and dealing with a phase space, which can be refined here, we really need to compare differential decay rates, and we need to compute the form factors over the range of allowed kinematics. Here, this is 3-body final state phase space, so there is a range of recall momenta for the pion, and we need to compute the form factors over the recall range. Of course, the complication is when we are in the finite box, we don't have access to all the momenta, but that's fine. We just need to compute the form factors. We just need to compute points over a large enough range. And nowadays, we can lean again in unitarity and analyticity constraints to have model-independent parameterizations of the shape. So all of that is well understood. But it is another piece of technology, another piece of theory that comes in, how to parameterize the form factors in a model-independent way. We don't want to make model-dependent assumptions. Oh, there's a vector meson that dominates the shape. That's okay for an exploratory calculation, but not for precision. Okay, so that's one complication. The other complication is that we don't have chiral perturbation theory anymore. So we don't, this is an outstanding problem. We don't have calculations of the electromagnetic corrections, period. There are no phenomenological estimates. There's also no lattice calculations. And this is really a hard problem. And it becomes even harder when you go to B mesons. So this means that for these lattice calculations, basically the electromagnetic corrections are the dominant source of error. Okay. So we had a project some years ago, a few years ago. We computed these form factors with awesome precision, sub-percent precision, all the same reasons why the kaon and pion stuff is so precise, using, again, model-independent parameterizations of the form factors. So the pure lattice calculation of these form factors, I would say, is kind of done. There are some puzzles. There are some differences with previous work here with the ETM calculation that one would like to understand a little bit better. But in principle, these calculations, the pure lattice QCD calculations, we understand how to do them, and we can really push them to the requisite precision. However, the QED effects are an outstanding problem. Okay, I'm going to skip through this because I am running out of time as per usual. This is just to show that once you have the form factors, then you can compare decay rates between theory and experiment, where the CKM matrix element floats, and out from the fit, then allowing the CKM matrix element to float, then gives us a determination of the CKM matrix element from fitting jointly the theory shape from the form factors with experiment. And you can also see how well the theory form factors agree with the experimentally measured shape. So that's, again, driven by QCD, and we should see that they agree with one another as they do here for the D meson case. And we have also good coverage over the entire kinematic range, and doing this different ways, we get the same answer. And I wanted to, I hope everybody in the back can see this. This is writing the same point here, that the CKM matrix element determinations are now driven. The dominant error is electromagnetic corrections. Lattice QCD is a subdominant source of error here. Okay. So, yes, let me finish this now. The last topic is a little bit more fun. This is rare decay. So this is a loop-induced decay. It doesn't happen in the standard model at tree level. It happens in the standard model at loop level. This also goes under the heading of flavor-changing neutral current decay. And for some reason, these are also known as penguin processes, because if you arrange the internals just right, it looks like a penguin. And that was a cute way to remember this when people first started worrying about this. So you always have to draw a cute penguin when you talk about rare decays. That's the context of that. And there's been a lot of theoretical work in working out the loop corrections and the higher order corrections and the matching conditions, and then different ways of extracting the relevant information from experiment, and how to phrase then this decay rate in terms of the hadronic parameters. So again, in the absence of radiative corrections, so photon radiation, we have this factorization, and all you need is a decay constant that we can compute in lattice QCD with an operator that now has a more complicated structure because it's a loop-induced decay. So there's a more complicated standard model expression here that goes into the standard model prediction for the decay rate. And you have CKM matrix elements as well that are encoded in here. And this is the standard model prediction shown here. And here's the error breakdown. So what is awesome about this is that the decay constant calculation is sub-subleading source of error. So that's a really nice achievement. What is also interesting is that the dominant source of error in this standard model prediction is the uncertainty in CKM matrix elements, in particular VCB. Well, that's still our business, right? You know, we compute you know, other form factors, etc., and confront these with experimental measurements to obtain a better determination of VCB. This other here includes structure-dependent QED corrections that I didn't write down, where there is some modeling involved, and that's why this error is larger than this, than the decay constant error. So in principle, we can beat down on this by doing a more complicated calculation. Yeah?
I had a question, why does this have anything to do with VCB, since I don't see a charm quark on this diagram?
Well, it's a loop-induced process, right? So,
The intermediate.
so it's the VCB is basically in here.
Yeah. Okay. Yeah.
I mean, VCB normalizes everything, right? So you have VTS and VTD in here, and yes, you have VTD in here, or VTS if it's a strange quark, which you then rephrase in terms of VCB, you know, using the using the usual parameterizations. So yeah, so that's where VCB comes in. It's a combination of CKM matrix elements, not just one. Yeah.
Why here we are looking at the four-fermion effective theory from left to right, but in the previous process we are looking at the four-fermion theory. Yeah. So from the left and the right we are looking at the four-fermion
Yes.
effective theory, but in the previous process we are not looking at this.
So I just didn't emphasize that. Here, the only reason why I have this written like that, emphasizing that here, is because the electroweak process, you know, is a loop-induced, and I'm only drawing one diagram. There are more diagrams, right? So there's a whole bunch of contributions, a whole bunch of diagrams that create B sub S decaying into mu plus mu minus at the quark level. And you can rephrase that in terms of these four Fermi operators. Again, there's a whole bunch of operators here. I'm not showing you any of the details. For the here I could have said the same thing, because there is no way, there's no sense in which the virtual W boson is, treated dynamically here, of course, but we're using factorization. So of course the virtual W boson just enters in these known factors as G Fermi. Okay? It's just a simpler structure. Here we have the V minus A structure, because it's a tree level decay. And in the loop process, it is, the structure of these operators is a little bit more annoying. Okay. But yes, it's the same thing. So we're not dealing with the W bosons dynamically in any way. Okay. So what are the practical consequences of this? So the rare decay rate has been measured and is being measured with increasing precision. For a while, it looked like the experimental measurements of the branching fraction were too low compared to the standard model prediction. So we'll see how experimentally this evolves. There's certainly still room here to develop a tension. We can always hope, right? But what is also interesting here is that the standard model prediction, the precision, is much better than current experiment. And in particular, for the B sub S, it is the LHC experiments that are going to continue providing information. For the B sub D, we will also get information from the Bell 2 experiment in Japan. B sub D to mu plus mu minus as they're accumulating data. So underlying this precision is this precision here, is the fact that the B sub S decay constant has been computed with sub% precision. So that's, so, you know, you can say you're welcome to our phenol colleagues and to the experimentalists. The reason why this is so well known is because of our community's hard work. Okay, I'm going to skip this because it's my calculation. You can ask me about this, but it's basically using the same methods as for light quarks as for heavy quarks, and we'll delve into this, the underlying principles, a little bit more detail when we talk about semantic EFT. The same principles allow us to push the calculations of decay constants to the same precision. And the problem, of course, is that the same caveats apply for the radiative corrections. In the case of the rare decay, some work has been done to compute them, and they are the limiting precision. But because it's a rare decay, it's still, we're looking at discovery, not at precision metrology, but doing the same thing for taking leptonic decay, charged leptonic decay measurements and confronting them with theory. We will also be, once the experimental precision reaches, we will also be stymied by the same issue with the radiative corrections, also for B mesons. And now, of course, it's a short hop and a skip to extend this to semileptonic decays of B mesons. And this is also treated in the FLAG report. Similarly, there's experimental measurements, and one can compare theory and experiment shape comparisons. And everything, of course, gets harder. There's a larger kinematic range that we can't quite reach. And so there's quite a long story about this that I won't go into here, other than that the experimental precision is just starting to come to the level where electromagnetic corrections are also relevant, in particular here. So this is certainly a beast that we need to deal with as well for semileptonic B meson decays. One of the reasons why VCB is such a big source of error is because there is another puzzle in VCB determinations. If you take form factor calculations, and they all broadly agree with one another, and combine them with experimental measurements of the differential decay rates for these exclusive processes, you get these values for VCB. You can also measure the weak decay of a B meson into charm final states inclusively, and use the operator product expansion plus quark hadron duality and some high order perturbation theory calculations to confront theory with experiment and extract VCB from an inclusive approach. And there is this 2 to 3 sigma tension, in particular troubling for VCB, because the theory underlying the VCB determinations in the inclusive case should be okay. So this is limiting. This is one of the reasons why you know, the CKM uncertainty for B sub S mu mu is so big. Of course, it depends, you know, what people choose here. And this is the reason why there is, you might have seen people trying to compute, or not trying, but working to compute inclusive decay rates, semileptonic decay rates in lattice QCD. And the things that Max was talking about, you know, going from few hadrons to multi-hadrons, the inclusive perspective, and of course Harvey is also one of the people who has been working on this, is an avenue towards that and might be an interesting way to resolve this. The question is whether this difference is experimental. You know, is there something in the experimental measurements that they don't understand? And there's some hints of that the sums of the exclusive processes, exclusive decays, don't match the inclusive ones. There might be some hidden channels. There can be, how do you identify a D star? You know, there's some modeling involved, some phenomenological understanding in identifying these also on the experimental side. So it gets messy. So there could be, this difference could be experimental in nature, or, you know, there could be a theoretical issue. And of course, us theorists need to go after the theoretical issues, and the experimentalists go after the experimental issues, understanding transitions to higher resonances as well might be another way in which we can figure that out. And for that, the work that the lectures that Max gave yesterday are, of course, very important. So as we delve into precision, there's, you know, always these puzzles that come in. Okay. There is another puzzle here that could be very exciting, but it's kind of been at a level that leaves us wanting more or less. But 3 sigma is kind of like a purgatory. You know, it's not conclusive. There is a 3 sigma tension when you look at lepton flavor universality testing ratios. So what this ratio is the rate of B goes to D star tau nu versus B goes to D star with a light lepton, an electron or a muon. So there's an interesting story here. When we have a tau lepton, there's another form factor that becomes a larger contribution. So this ratio is actually needs to be computed in lattice QCD. And here you can see the standard model prediction, which includes lattice QCD form factor results that should be acknowledged better than they are. And the experimental situation certainly looks a little bit messy. There's certainly experimental measurements that seem to be entirely compatible, at least with the RD star, but the average for in the RD star plane has this 3 sigma tension that was 4 sigma for a while, but never has exceeded 5 sigma and has been with us for a good 10 years now. And, you know, this could be exciting because the tau lepton decay, lepton flavor universality, modulo, of course, phase space, etc., should hold in the standard model. And if it doesn't, that might be because of, you know, there's something else that couples preferably to tau leptons than to light leptons, for example. That could be an explanation for this. But this tension is not large enough and not significant enough to get people super excited, but it is one of the flavor anomalies that hasn't gone away and has been stable. And just as a general overview, another way of phrasing CKM unitarity is in this unitarity triangle. So this is the unitarity triangle that probes CP violation. So the amount of CP violation is determined exactly where where this point in the triangle is. And you can see, I kind of showed you the 10-year skip before, and here you can see how the precision improvements in lattice QCD in the last 10 years have changed the bands. Now, some of them have improved because of experiments. So these angle bands here, like sine 2 beta, that's basically experimental measurements that have improved. But mixing is, the errors are dominated by theory, and this change here is coming from better theory. Same for epsilon k, and also same for VUB. The dominant improvement comes from better quantified form factors. On the experimental side, not that much has changed. So you can actually measure, you can actually visualize the impact of lattice QCD calculations by looking at the evolution of these of plots like this. And that's why I'm showing it. Okay, so this is my final slide that I wanted to show. Again, as part of the big picture overview, I've emphasized what we might call lattice QCD flagship results. And, as we move on, this is becoming more and more crowded. But there's a whole space of lattice QCD calculations where, we're having fun exploring new methods and sharpening our tools. But of course, eventually these things, we want to move them back into flagship status, which means that we have well-quantified results. All the errors the systematic errors are under good control. Of course, one can always improve some of them. And for many of them, we have exceeded the precision to where now structure-dependent QED effects become relevant. Okay, and as I will discuss on Friday, these quantities are relevant to the mu on G minus 2, and I'll explain them a little bit. And these are rapidly moving towards flagship status, which is very exciting. Okay, I think this was supposed to be the first half, but I guess I always talk for longer. I always find more things to explain. So maybe we can stop here, and I'll take questions before the break, if there are more questions. Yeah.
So for the QED correction to those meson big decay, so do we only need to consider the QED corrections coupled to the mesons, the quarks in the mesons, or do we need to consider the corrections on the vertex or the mu leg?
Very good. So the answer is yes, and yes, and yes. By structure-dependent corrections, I do mean QED corrections that depend on the underlying structure. So it's the charge distribution inside the hadron that, that makes it difficult. That's why it is why we need to do a non-perturbative calculation. If we know how to treat, we know how to treat the pion as a point-like particle, and computing, QED corrections of point-like, that scalar QED, you can take that to many orders. That's well known. Those corrections can be included easily, but it is when the pion when the pion is not a point-like particle, when it has structure, and that structure comes from non-perturbative QCD, this is why QED corrections are also a non-perturbative problem. And yes, when we have chiral perturbation theory, you know, we have some access to this, but in the absence of chi-PT, we need to do this within. I think lattice QCD is the only. Maybe some dispersive treatments can help there too. I think there are some ideas for that as well. But yes, virtual corrections as well as radiative corrections, the usual thing. You have to add everything together to have something that is well-defined.
Since you mentioned the lattice QCD contribution in the RD star prediction, so what exactly was involved there? So you mentioned, so for the tau especially, the tau final state, then you need the form factor.
Right, right,
Yeah.
right. So if you let's start with B to D. You know, there's two form factors, which we usually call F plus and F naught. And for the when you write down the decay rate in terms of the matrix element, in terms of the form factors, then the F naught form factor gets something like, you know, it's the helicity suppressed one. So in the decay rate, this is multiplied by the lepton mass squared. So in, you know, when we look at B goes to D or D star, mu or electron nu, then the contributions from, say, the scalar form factor are suppressed, helicity suppressed. So basically, experimentally, they're not accessible, especially, you know, for B meson decay. And you can see it a little bit, I think, with enough precision for, you know, charm decays. But really, not inside the errors. But the tau lepton, of course, really changes the phase space and really also changes the, you know, in the tau lepton, you cannot neglect the contribution. And that means when you look at the ratio, that the numerator will have a contribution from F naught and the denominator basically doesn't. The numerator being tau. So the ratios of RD star are the branching ratios of B goes to D or D star tau versus B goes to D or D star light. Let me call it like that. Okay. And so in the numerator, we'll have the form factors that are helicity suppressed in the rate, both in the case of the D or the D star, and in the denominator, we don't. So when constructing this ratio, you know, we get some access to these form factors from just how these are related to the matrix elements. So kinematic constraints relate these form factors to each other, you know, at q squared equal to 0, etc. So when you do the phenomenon, you know, when people do the phenomenological calculations, they can use those constraints to get some information about these unknown form factors, but really you should compute them. You know, you need to, in order to really have a good standard model prediction of these ratios. You know, people compute these ratios. The background is experimentalists look at these ratios to avoid, and phenomenologists look at these ratios to avoid QCD. Like, how can we minimize the impact of needing to know the form factors. The point is, for these tau to light lepton, the ratios, one does need to rely on lattice QCD form factors. Not sure if that was your question. Yeah.
So on the right-hand side of that plot, on the complexity side where not everything is totally clear yet, could you list some of the problems that lattice QCD has?
You mean other than?
Yeah, rather like for those processes, what are the issues lattice faces for computing those things?
Okay, so I think for inclusive decay rates, it's a matter of fully developing and understanding the formalism, I would say. So this is very similar to what Max was telling you about. So understanding multi-hadron systems in lattice QCD means that we need to understand how to turn our finite volume, Euclidean finite volume calculations of whatever quantities we compute. We need to know the formalism for how to take those results and turn them into physical infinite volume Minkowski space results. So I think that's the theme pretty much almost for everything that's more complex, apart from the computational difficulties. And this is where there's also been an explosion of activity and methods. For things like parton distribution functions and related, there's a whole acronym soup of quantities. I think one of the crucial insights there was, again, developing an EFT framework that allows access to something that is, lives on the light cone, basically. So how do you get access to that from a Euclidean lattice QCD calculation? By phrasing it smartly as a limit of quantities that can then be computed for a variety of large momenta and then taking a different extrapolation. So all of these more complex quantities typically require different kinds of extrapolations, not just right, continuum, etc. I think that's one way to broad picture the map here. Very good question.